Hey guys, welcome to this week's lecture. This week we're going to be talking about 4.6 related rates in the textbook. And so just a little preface to this lecture. So in addition to these lecture videos that I'm doing, I also linked this guy, the organic chemistry tutor. He does a bunch of examples on related rates. And these types of problems really take a lot of practice, and they can be, kind of weird when you first see them and, when you first start working with related rates. But the more you practice, the better you get at these things. And, this is pretty much like after this week, it's gonna get a little bit less intense. So there is light at the end of the tunnel. Just wanted to let you guys know that. Okay, so all right, so let's get into it. We're going to talk about how we can use derivatives to find instantaneous rates of change in real life. And when we talk about rates, what we are meaning is how something is changing with respect to time. Okay, and so I have this little example right here. We have this balloon that is being blown up, and at time 1 it looks like this. Maybe after 2 seconds it looks like this. After 3 seconds it looks like this. And there's two things that are changing at the same time. The first thing that's changing is the radius of the balloon, right? It's getting bigger and bigger as time goes on. And the second thing that's changing is the volume of the balloon, how much air the balloon can hold. So those two things are changing, and what we're trying to do is we're trying to relate these two values with an equation so that, we can figure out the rate of the other quantity, okay? And we're going to do several examples with this, but like I said, the organic chemistry tutor, he does like 15 or 20 examples. I mean, it's like a really crazy long video. And I want to say they're all different from mine. I didn't watch the whole thing, but the examples that I have, come from a textbook. So I don't know. Maybe some of them are the same flavor, but you guys should check him out. He's really good, and especially if you need more practice with this kind of stuff. All right, so what are related rates? So I just kind of alluded to this with the balloon. So related rates involve two or more variables that change at the same time, but possibly at different rates. So like, the balloon, we had two variables. We had the volume and the radius. We're both increasing at the same time, but at different rates. And so the key idea that we're going to be using here is if we can come up with a formula with both variables in it, and if we know how fast one of them is changing, so if we know the rate of one of them, then we can figure out the rate of the other one. So, for example, in this balloon problem, if I knew that the radius was changing at, let's say, 1 centimeter per second, if I knew that, and if I knew that the radius was 8 centimeters, from that information, I could figure out how fast the volume is changing. And of course, the volume given the radius. All right, so let's look at some examples of quantities that are related before we start doing the problems. So we kind of just talked about this one. The volume of a balloon, V, and its radius, R, are both increasing as we blow it up. And we can, if we assume that a balloon is a perfect sphere, we can use the volume of a sphere to relate the radius right here with the volume. So these two are related by this formula. Let's see. So increasing a rectangle's length, L, is related to its area, A, by the formula A equals length times width. So if we increase a rectangle's length, then its area will increase as well. And area and length are related by this formula right here. We're going to do a bunch of examples with by using Pythagorean theorem. And so in a right triangle, if we have legs A and B and hypotenuse C, we have this relationship. A squared plus B squared equals C squared. So that's how those are related. So let's actually do some examples here. All right. So the way that I like to tackle these is just to start writing whatever I know and what I need. That's the first thing you want to do here because, as I said, these take practice. I know this is kind of a difficult concept in calculus to grasp, but I promise you the more you practice, the better you're going to get at these things. And and it's not going to get any harder than this in Calc 1. Okay, so let's look at this. A spherical snowball melts in such a way that the instant at which its radius is 20 centimeters. All right, so I'm going to highlight this important stuff. Its radius is decreasing at 3 centimeters per minute. Okay, all right. And then it says, at what rate is the volume of the snowball changing at that instant? So we need to figure out what we're looking for. The last sentence is telling us that. We're looking for the rate at which the volume is changing, okay? So what does that mean? We're looking for dV, the change in volume, dt, with respect to time. That is what we were interested in ultimately. And with all of these problems, we're always trying to figure out the change in the quantity with respect to time, okay? So, okay. All right, so we have that. Now they tell us that the radius is 20 centimeters, so let's go ahead and just write that out. We're interested in that exact instant when the radius is 20 centimeters. And it says that the radius is decreasing at 3 centimeters per minute. So since it's decreasing, the rate is decreasing, we're going to tack a negative on there. And what's decreasing? Well, we're looking at the change in the radius, r, with respect to time, t. So this is the rate at which it's decreasing. And since it's getting smaller and smaller, we're going to tack a negative here. Negative 3 centimeters per minute. And this is really all we need. Okay, so this is everything that the problem actually tells us. They tell us the change in the radius with respect to time. They tell us the radius at the instant we care about is 20 centimeters. And it says that we're looking for how the volume is changing with respect to time. And we should expect that this would be a negative value, right? Because as a snowball melts, the volume is getting smaller and smaller and smaller. So we do expect this to be negative. Now what we need to do is we need to relate radius and volume with a formula. Well, how about the volume of a sphere? So the volume of a sphere is this guy, 4/3 pi r cubed. So this is very much like implicit differentiation, what I'm about to do. It is implicit differentiation because at the end of the day, we're going to be using the chain rule. And I'm going to show you, what it looks like under the microscope a little bit for this problem, but I'm going to skip some of the details in the next examples just to, get a feel of how this works. Okay. So, what am I going to do with this? Well, the first thing you need to assume is that the radius and the volume are both functions of time, okay? And that's told to us in the problem. Basically, the radius is decreasing at 3 centimeters per minute. And they're asking us, at what rate the volume is changing as well at that instant. So the radius is a function of time, okay? And so what we can do is, and I'm just going to do it for this problem, all right? So the radius is changing with respect to time. So instead of r to the 3, I'm going to say this is r as a function of time to the 3rd power. So I just want to show you, what what's happening here. Okay, so now what we're going to do is we're going to take the derivative of both sides with respect to time, okay? Because that's what we're interested in. We're interested in the change in volume with respect to time. So if I take the derivative of the left side, I get dv dt equals, and let's take the derivative of the right side. So the first thing I'm going to notice is that I have a function within a function, basically. I have the function r of t to the third power, okay? So remember what the chain rule says. The chain rule says that if we're trying to differentiate, a nested function, something like this, if we're trying to differentiate something like this, well, then the way that we do that is we do the following. We do f prime of g of x times g prime of x. This is the chain rule right here. Okay? So that's what we're doing here. Just like implicit, just like implicit differentiation, what we're doing, these constant numbers can just kind of stay there. But here, what we're doing is, well, we're first taking the derivative of the outer function, okay? So this is going to be 3 r of t squared times the derivative of the inner function. Well, the derivative of r of t is just dr dt, right? Okay. And then because r of t, we know that the radius is a function of time, we can just leave it as r. And I know this looks a little bit convoluted, but I'm not gonna do this part every single time. I just want to show you that the chain rule is happening here. All right, so let's do dv dt. And then I'm going to go ahead and simplify this guy on the right to give me dv dt is equal to, well, let's see, those 3's cancel out, and I'm just left with 4 pi r squared dr dt. Okay, now I can plug in what I know. I know dr dt is negative 3 centimeters per minute. I know that r is equal to 20 centimeters, and I'm going to leave my units in here just to show you what's happening, but in future examples, I'm not going to do all of that work. Just want to show you that this is a thing that's happening here. And then dr dt was negative 3 centimeters per minute. All right, so let's see what this is going to give us. If I do the squaring, what I end up getting is 4 pi times 400 centimeters squared times negative 3 centimeters over 1 minute. And then if I just multiply the numbers in the numerator, 4 pi, 400, and negative 3, I end up getting about negative 15,080. Okay, and then centimeter squared times centimeter is centimeter cubed all over minutes, okay? So the volume, dv dt, which we were looking for, is decreasing at a rate of negative 15,080 centimeters cubed per minute. And the reason I left the units in here was to show you that, with volume, we're always going to get an exponent of 3 when we're looking for the change in volume. Okay, let's do another one. And I encourage you guys to pause this video and see if you can do it yourself. Because, like I said, these take practice. All right, so let's see what they're telling us here. It says a spherical balloon is being filled with air at a constant rate of 2 centimeters cubed per second. How fast is the radius increasing when the radius is 3 centimeters? Okay, so it's being filled with air, so we know that our rate should be positive. And look what they give us. They give us 2 centimeters cubed, okay, a rate of volume. So what do they give us? They give us dv dt, right? Volume over time. And that is, I'm just going to put 2. I'm going to be lazy from here on out, okay, with the units. Now it says, how fast is the radius increasing when the radius is 3 centimeters? Well, they tell us the radius is 3 centimeters, and we want to know how fast the rate at which the radius r is increasing with respect to time. That's what we want to know. All right, so now we can use the same formula that we used before with the snowball. We can relate volume and the radius because, those are the 2 things we have, basically. And it was 4/3 pi r cubed. All right, so now what I'm going to do is I'm going to take the derivative of both sides with respect to t. So I get dv dt, and from here on out, I'm going to be lazy. I'm not going to do the whole chain rule. Using the power rule here, I get 4 pi r squared, and then just like with implicit differentiation, I'm tacking on dr dt because I differentiated the radius with respect to time. All right, so that's what I have. And now what I'm going to do is just plug in what I have. I have dv dt equals 2, so I'll plug that in there. My radius was 3, so I'll plug that in here. And I'm trying to solve for dr dt. Well, all I have to do is divide both sides by this mass. So I get dr dt is equal to 2 divided by this mass. That's 9, okay? And my units, well, the change in the radius is in centimeters, and time was in seconds. So my unit should be centimeters per second. Okay, so let's do this. We have 2 divided by 36 pi, and we get approximately 0.018 centimeters per second equals dr, change in radius with respect to time. And notice that on top I have centimeters for my radius, and on bottom I have seconds for my time. If x squared plus y squared equals 25 and dx dt equals 5, find dy dt when, first of all, x equals 3, and second of all, x equals 4. So whenever you're given a formula that relates the two, we can go ahead and we can go ahead and take the derivative of both sides of the formula. So let's go ahead and do that. So what are we given? We're given x squared plus y squared equals 25. So a circle centered at the origin with a radius of 5. That's what that is. And, okay, and so I'm going to just start, because they gave us a relationship here, I'm just going to go ahead and differentiate this guy with respect to time. That's what we're doing for this whole unit. And fill in the missing information, okay? So with respect to time, we have 2x, tack on a dx dt using the power rule, plus 2y, tack on a dy dt again, equals, well, the derivative of 25 is simply 0, okay? So now we're looking for dy dt. We're looking for this. And we are given dx dt, so we have that. We're given x, we have that. We need to figure out what y is. Well, we're interested in what happens when x is equal to 3 first. And so to get y, I'm just going to plug in 3 into my relationship here for x. So when x is 3, what is y? That is our question here, so we can plug everything in. Well, if I subtract 9 from both sides, I get y squared equals 16, therefore y equals 4. All right, so 4 is going in there, and I have everything I need. I have y, I have dx dt, and I have x. And now I'm going to just, well, actually what I'm going to do first is, I'm just going to isolate the dy dt by first subtracting 2x dx dt from both sides of the equation. And then I'm just going to divide both sides by 2y. So I'm just going to write it like this. And those 2's cancel out. So I have negative x over y. All right, so there we go. Now let's plug in everything we know. So dy dt is equal to negative x over 4 times dx dt, which was 5. We're not given units here, so I don't have to worry about them. All right, so what am I getting here? I am getting negative 15 over 4. That's dy dt. So that was when x is equal to 3. Now for x equals 4, y is also going to change here. So we still know dx dt is still going to be 5, whatever the units are. X is going to be 4. Y is going to be, well, again, we're just using this relationship here that says that x squared plus y squared equals 25. Y squared equals 9, therefore y has to equal 3 in this case. Let's put that here. And again, I'm just plugging in my values into my derivative that I took, which was right here, right? I isolated dy dt, so all I have to do is plug in my new numbers, and I get negative 4 over 3 times 5, which is just going to give us dy dt equals negative 20 over 3. And that's my answer for part B. So d equals 2 sine of pi t is the vertical displacement in feet of an object at time t in seconds. How fast is the object moving initially? So let's go ahead. We're given a relationship between displacement and time. So let's just go ahead and take the derivative of both sides with respect to time. So on the left, I have the derivative displacement with respect to time. And on the right, what's nice here is, well, you'll see. Okay, so 2 sine pi t. I have to use the chain rule here. So it's just going to be 2 cosine of pi t, the derivative of the outside, times the derivative of pi t, which is just pi. Okay, and now what I'm tacking on, I'm taking the derivative of t with respect to t. So basically, that's going to cancel out. So that's nice. So all I have to do here, I'm looking for the change in distance over the change in time. So all I have to do is plug in my t values because I already have isolated what I need. So initially t is going to be 0. So dt is equal to 2 cosine pi times 0 times pi. Well, the cosine of 0 is 1. And this is going to give us 2 times 1 times pi. So this is just 2 pi is my change in distance over time. Now, what are my units here? Well, they tell us the units of distance are feet, and they tell us the units of time is seconds. So this is going to be, my units are going to be 2 pi feet per second. Okay. All right, so same thing. We're just plugging in t equals 5 into our derivative that we found up here. All right. So in this case, we have the change in displacement over the change in time is 2 times cosine of 5 pi times pi. Well, the cosine of 5 pi, that's an odd multiple of pi. The cosine of pi is -1. So what we're going to end up getting here is negative 2 pi. And again, our units are going to be feet per second. So this is my dd dt, the change in displacement with respect to time in that case. A cube is being increased in size such that the length of each edge is increasing at 0.1 centimeters per second. Find the rate at which the surface area and the volume of the cube is increasing when the side length is 10 centimeters. So let's go ahead and draw a picture. And again, I encourage you to pause the video and see if you can do these, or see if you can get a picture going. So here's my cube. Now in a cube, all the sides are the same. That's important. So all the sides are going to be x. The height, back, front, all of these sides are going to be x. And they tell us that the side length is 10 centimeters, which is just x. Maybe I'll do this in a different color. So we have this information. What are we looking for? We're looking at the rate at which the cube is increasing. First, we're looking for the surface area. So I'm looking for the change in surface area with respect to time first. And I'm told that each edge, each side, is increasing at 0.1 centimeters per second. So what does that tell us? What's changing? X is changing. So that tells me that dx, the change in x with respect to time, is 0.1 centimeters per second. Okay, and I think that's all the information we have. Okay, since we're looking for surface area, let's go ahead and find the surface area of a cube and write that formula down, because that's going to relate the sides and the area. So what is the surface area? The surface area is literally just the areas of all these faces on the cube added up. So how many faces on the cube do we have? Well, we have 6 of them, right? And what's the area of each face? Well, the area of, each face is just going to be x times x, because the length and the height are both x. So x times x, length times width, if you like thinking about it like that. But at the end of the day, this is just going to give us 6x squared. I'm just going to write this. All right, so this is good. Good news. We have area and the sides related, and we have a side, and we have the change in the sides with respect to time. So let's go ahead and do what we do and take the derivative of both sides with respect to time so that we can find dA dt. So dA dt is going to equal, just using the power rule, I have 12x dx dt. And now I can just plug in my missing information. So I know x is 10, I know dx dt is 0.1. And again, I'm being sloppy with the units here, but you don't have to be. So this is just going to give me dA dt is going to give me a rate. So this is the rate. It's going to be 12 centimeters squared, because we're looking at the change in area. Area is always squared, so centimeters squared per second. So this is the answer to the first part. Now for the second part, I need to figure out the rate at which the volume is increasing. Now the volume, let's write down the volume of a cube. Well, the volume is just going to be the area of the base times the height. The area of the base is x squared, x times x, and the height is x. So the volume of the cube is just x to the third. Taking the derivative of both sides, we're trying to find dV dt, so the derivative of volume with respect to time on the left is equal to 3x squared tack on a dx dt. and then plug in my missing information. So 10 and then 0.1. So let's see what we get here. That's going to be 30, right? Yeah, okay. So dV dt is going to be 30. Now, since I'm looking at the change in volume, I should expect centimeters to be cubed per second. So that is the answer to the second part. Okay, and that is pretty much it. I will see you guys in the next video. Thanks for watching. A cylindrical tank with radius 5 meters is being filled with water at a rate of 3 meters cubed per minute. How fast is the height of the water increasing? All right, so the first thing we want to do is, figure out our given information. So we're given that the tank has a radius of 5 meters. And then they tell us that they fill it with water at a rate of 3 meters cubed per minute. So meters cubed, this is telling us that this is a change in volume with respect to time, because anything cubed is volume. So what we have is we have dV, the change in volume, with respect to time, which is 3 meters cubed per minute. Okay, so that's one of our rates that we have. And the question is, what we really want to know is how fast, okay, so we're looking for a rate, how fast is the height of the water increasing? So what are we looking for? Well, we're looking for dH dt, the change in height with respect to time. All right. So the first thing I want to do is I want to come up with a formula that relates height and volume. Well, how about we just use the volume of a cylinder? If we have a cylinder, let's just draw it. Here's our tank. Here's our cylindrical tank. Our height is how tall it is, and our radius here is 5 meters. Okay. Now, the volume of a cylinder is going to be the area of the base. The base is a circle, so it's just pi r squared times the height. All right. So here is my relationship between volume and height. All right, so I'm in a good place so far. And now what I need to do is I need to take the derivative of both sides. So if I take the derivative of the left side, I just get dV dt. And if I take the derivative of the right side, well, I have a product. I have pi r squared times h. So I need to use the product rule because I have two variables, r squared and h, with pi being the constant in front of r squared. So let's use the product rule. So the product rule says keep the first times the derivative of the second. Well, what's the derivative of h? It's just dH dt. With respect to t, of course. All right, keep the first times the derivative of the second, plus now you keep the second times the derivative of the first. Well, what's the derivative of pi r squared? That's just going to be 2 pi dr dt. Okay? And now this is going to be a problem that is a little bit different from the other ones because we're looking for dH dt, but we have a dr dt in here, which is strange. But the key thing to notice here is, the context of the problem. It's saying that this cylindrical tank is being filled with water. Okay, so maybe, I don't know, there's our water right here. It's being filled with water. And the key thing to notice is that the radius is not changing with respect to time. The height is, right? Because as we fill in more and more water, the water level is going to rise. So the height is definitely changing with respect to time. But the radius is definitely not changing, okay? The radius is going to stay the same because we have a uniform shape. It's just, the cylinder doesn't change no matter how high you are. So that's the key observation here. That's what makes this problem different from the other ones, is that in this case, the change in the radius with respect to time is nothing, okay? Because the radius is constant. And so I'm going to show you one way to do this. The first way is we could have just plugged in the radius from the get-go. Because it's constant, we are allowed to do that. But we can also see it like this. So let's plug in everything that we know here into this guy, because ultimately we're trying to get dH dt. So we have dV dt is equal to, well, our radius is 5 meters, and so we have pi times 5 squared times dH dt, which we're looking for. And now, they don't even really they don't tell us what the height is or anything. So the key observation, though, is that we don't need the height because all of this right here is being multiplied, and dr dt is equal to 0. So h times 0, that's just 0. So this whole thing goes to 0, and this is what we're left with here. dV dt equals pi 5 squared times dH dt. Now, dV dt we were given as 3 meters cubed per minute. I'm just going to put in 3 here because I'm a little bit lazy, and we'll remember our units at the end. And so if I divide both sides by 5 squared pi, or 25 pi, I get that dH dt is equal to 3 over 25 pi. Now, my units, this is, we're changing the height with respect to time. So it's going to be the change in meters, because meter is our length unit. The change in meters per minute. So this is my answer. dH dt is equal to 3 over 2 pi meters per minute. So the key thing here is that the radius, as the water level rises, the radius is always the same. It's constant. And so, that's why dr dt is equal to 0, because the radius is not changing with respect to time. Okay? Now, we are going to do a problem towards the end of this where, both the radius and the height are changing, and we'll see how to do that. But with a cylinder, pretty simple object, we're good. Okay. So let's do this. This is a really classic related rates problem that everybody does in calculus classes. So we have a 3-meter ladder stands against a high wall. So I'm just going to draw it. Here's my ladder, and it's 3 meters. And it's, resting against this wall. There it is. The foot of the ladder, that's this part. The base, this is the foot. The foot of the ladder moves outward, okay, so it's moving that way, at a constant speed of 0.1 meters per second. Okay, so, usually in our right triangle, we call the base x and we call the height y. Well, I do anyway. And so when they tell us that the ladder is moving outwards at a speed of 0.1 meters per second, they're telling us information. They're telling us dx, the change in x with respect to time, is equal to 0.1 meters per second. And it's positive because the change in x, basically the distance between the ladder and the wall, the x coordinate, is getting larger and larger and larger. So that rate of change is a positive 0.1 meters per second. Then they tell us when the foot is 1 meter from the wall, okay, that tells us when, let's just write it down, when x equals 1, that's what that means. How fast is the top of the ladder falling? Okay, fast. We're looking for a rate. Is the top of the ladder falling? So what are we looking for? We're seeing, how fast this ladder moves downwards. So we're looking for dy dt. So what is dy dt when x is equal to 1? That's what we want to know. And then they ask us a second question, which we'll do at the end, but it says, what about when the foot is 2 meters from the wall? So that's, when x equals 2. But so far, this is the information that we have so far. Now let's go ahead and relate x and y through a formula. Well, what formula do we know about lengths of triangles and right triangles in particular? It's the Pythagorean theorem, right? Now, we have x squared plus y squared equals the hypotenuse squared. And notice that the hypotenuse, the length of the ladder, isn't going to change. Now, the distance, from the base to the wall is going to change. The vertical height of the ladder is going to change. But the ladder itself is always going to be 3 meters, and that's why I'm not making this a variable. All right, so now we have a nice little equation relating x and y. And so now what we're going to do is we're going to take the derivative. And so how do I do it? Well, again, I'm taking the derivative of both sides with respect to time. So I get 2x dx dt plus 2y dy dt. Now the derivative of a constant is 0 on the other side. And now what I'm going to do is I'm going to make this look a little bit cleaner and just pull out an x at first. Not an x, I'm sorry, a 2. I'm just trying to condense this as much as I possibly can. And if I divide both sides by 2, I just get x dx dt plus y dy dt equals 0. Okay, so I have x, I have dx dt. All I really need here to be able to solve it is y. So what is y? Well, we need to use Pythagorean theorem, right? So y, we have our triangle. We're interested in what's happening when x is 1 and our hypotenuse is 3. So what is y? Well, we just do 1 squared plus y squared has to equal 3 squared. Therefore, y squared is equal to 8. Square root both sides, and y is equal to the square root of 8. We would usually do plus or minus, but we're dealing with lengths here, real world situation, so that's going to be just a positive root 8. So that's our other key piece of information that I'm going to add to this list up here. Because we need it, right? We need it to plug in right here. So let's plug in everything we have. X is equal to 1. Dx dt is 0.1. y is root 8, and we don't know what dy dt is. So let's go ahead and find it now. What I'm going to do is I'm going to subtract 0.1 from both sides to get root 8 times dy dt is equal to negative 0.1. And then I'm going to divide both sides by root 8. And I'm going to put this in the calculator and include units. So this is the rate at which the height is changing with respect to time. So our units are going to be meters per second here. The change in the height over time. Now notice that our answer here is negative, which should make sense, right? Because this ladder is going farther and farther down the wall, we expect that the speed is going to have a negative sign to indicate that like basically that the height is getting smaller and smaller and smaller. Okay, so we got that. So that was when x equals 1. And they asked us, the second part of the question said, what about when the foot is 2 meters from the wall? Well, the only thing that's going to change here is x and y, right? If x changes, y changes as well. So let's do that second part, and I'm going to go ahead and erase this and get our new values. So when x equals 2, if we apply Pythagorean theorem with x equaling 2 instead right here, well, what do we get? Let's see. Okay, so we have 2 squared plus y squared equals 3 squared. And so we get y squared equals 5. Therefore, y is equal to the square root of 5 when x equals 2. So that's our new information. And we can take that new information and just plug it in the same exact thing that we had over here. So the only thing that's changing is this is now a 2. And this is now a root 5. So solving for dy dx, let's see what we get. Or dy dt rather. Didn't mean to say dx there. But okay, let's see what we get. So if we subtract, let's see, this is going to be 2/10 from both sides. So we have root 5 times dy dt is equal to negative 0.2. And then we're going to go ahead and divide both sides by root 5. So we get dy dt equals negative 0.2 divided by root 5. And in the calculator, let's see what that is. We get about negative 0.089 meters per second. So this was when x equals 2. That was the change in the height with respect to time. And remember, when x equals 1, we had negative 0.035 meters per second. Okay. So the second part of this question says if the foot of the ladder moves out at a constant speed, how does the speed at which the top fall change as the foot gets farther out? Well, we can just look at this example to see what's happening. Basically, we sort of did something like that here. we had this is the closer, when the foot is closer to the wall versus when the foot is farther out. And, well, what's happening? I mean, the speed is increasing, right? I mean, even though this is a negative number, remember, this is a velocity that we're looking at, distance over time. And velocity is just speed with a direction attached to it. So the answer to this is that the farther, and we can, look at the actual formula. Actually, let's do that. So what did we have? We had dy. Let's just go back to this part before we plugged in numbers. So we have x dx dt plus y dt equals 0. So that's what we have. This is just the general formula before we plug anything in. And, what are we interested in for this question? We're interested in the speed at which the top falls. We're interested in isolating dy dt to see what's going on. So if we subtract x dx dt from both sides and divide by y, I forgot the x here. So we get y dy dt equals negative x dx dt. And finally, dividing by y, we get dy dt equals negative x over y dx dt. Okay? And so this is how, you can really see what's going on here. This guy is a constant, a constant number, so we can pretty much ignore it. And so we want to just look at the relationship between x and y, right? And that's what we did in this example right here. When x is equal to 1, we are getting this for dy dt. When x is equal to 2, we get this. And so what we can say with confidence is that as x increases, the speed, so, how fast the ladder is falling, the speed at which the ladder is falling vertically is increasing. Okay? So that was that example. Very classic problem in calculus, this problem of the ladder falling, sliding down a wall, basically. All right, let's do this example here. So let's see. It says the altitude of a triangle is increasing at a rate of 1 centimeter per minute. All right, so we're given a rate. Now, let's first, remember what the altitude is. The altitude is basically another word for height. So that is our altitude, h. So what I'm just going to say, instead of dA dt, I like h better for altitude. I'm going to say the altitude with respect to time, the change in altitude with respect to time, is 1 centimeter per minute. All right. Then they tell us that the area of the triangle is increasing at 2 centimeters squared per minute. So dA, the area with respect to time, has an increasing rate of 2 centimeters squared per minute. Okay. It says, at what rate is the base of the triangle, at what rate is the base, okay, I don't know why base of the base, that's weird. Let me erase that. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 centimeters squared? So let's see. All right, so we have the altitude is 10 centimeters and the actual area is 100 centimeters squared. Okay. Now, I just want to really harp on this because it's super important and it's something that a lot of students have misconceptions about. We don't want to plug in the H and the A values as if they're constant first. We want to differentiate and then plug in. Because if we have this area formula relating, height or altitude, base, and area, the area of a triangle, we have this formula, 1/2 times base times height. And so you might be tempted to plug in 100 for A and 10 for H and then differentiate. But that's not right, okay? Because the reason that's not correct is because what you're assuming is that the height and the area are fixed when you do that before you differentiate. And we don't want to assume that. Okay, because, it's telling us that both of these quantities are changing. So, but, however, we are going to have to find the base, and that is, we can use this formula to find the base because we're not differentiating it. We're just seeing, well, what's the base when the height is 10 centimeters and the area is 100 centimeters squared? That doesn't say anything about, how it's changing, basically. So, okay. Anyway, that was long-winded, but let's go ahead and differentiate this thing. So I'm going to differentiate both sides with respect to time. And on the left side, I get dA dt. And on the right side, I have to do the product rule. Right? Because I have 1/2 times base that I'm going to be differentiating with respect to t, and I also have h. So let's go ahead and do the product rule here. We keep the first times the derivative of the second. Derivative of h is just dh dt, plus, now you keep the second, times the derivative of the first. Well, what's the derivative of 1/2 b with respect to t? Well, it's just going to be 1/2 dB dt, which is what we're looking for. We want to know what is the change in the base with respect to time. All right, at what rate is the base of the triangle changing when the altitude? Yeah. Okay, so notice that we have everything that we need to plug in here to solve for dB dt, except b. And that's what, we use here to find b. The area is 100, so we'll plug that in for a. 100 equals 1/2 times b times h, which is 10. And 10 divided by 2 is 5. 100 divided by 5 is 20. So our base is equal to 20 centimeters. So let's plug everything we have in. dA dt is 2 centimeters squared per minute. Then we have 1/2 times 20 times dH dt, which is just 1 centimeter per minute. I'm being lazy with units, but you can leave them in if you want. And then we have h. We already differentiated this, so now we can go ahead and plug in our variables. H is equal to 10 times 1/2 dB dt. That's what we're trying to isolate. So I'm going to just simplify this thing more, and I'm going to write it more here. This guy becomes 10 10 times a half, well, that's just 10 divided by 2 is 5 dB dt. Okay. Subtract 10 from both sides to get what? -8 equals 5 times dB dt. And finally, we're going to divide both sides by 5 to get dB dt is equal to -8/5, which ends up, let's see what this is. So this is going to be -1.6. Now, a base is length, okay? So what is this? What are the units here? Well, this is going to be, our units were centimeters, and our time unit was minutes. Okay, so this is our final answer right here. Let's see where we're at. Okay. All right, so, and I encourage you guys, pause these videos, try to do as much as you can and see if it, matches up with what I'm saying. All right, so 2 cars start moving from the same point. So here's our point. One travels south at 60 miles per hour. Okay, what does that tell us? Well, this is a rate, right? Distance over time. So this is going to be our vertical rate. And so what I'm going to call that is dy dt. And I'm going to say it's 60 miles per hour. All right, and it's going south, so it's going directly down. The other one is traveling west at 25 miles per hour from that point. So that's going to be, like my x value. This is my y because it's vertical. And so my dx dt is going to be 25 miles per hour. Okay, so then it says, what rate is the distance between the cars increasing 2 hours later? What rate is the distance increasing 2 hours later? Okay, so what are we looking for? Well, so here's car 1. Oh man, I can't draw a car. Too much pressure. Yeah, I know you guys are going to laugh at this. This is a really bad car. But that's car 1, okay? And then here's car 2. Let me do him in green or something. Let's see. See, this is why I did not go into the arts. And what we're trying to see is the distance between these two. So this guy, this is the length between those 2 cars. And we're looking for the rate, okay? The rate of that distance. So if I call this distance c, what we're interested in, what this is asking for, is dc dt. It's asking for the change in the distance between the cars with respect to time. Okay, so we're looking for a rate. Now the question is, we know we're going to have to use Pythagorean theorem because we have this right triangle business going on. But, if we think ahead a little bit, we're going to have to plug in x and y eventually. And so, maybe let's think about that. Like, how would we figure out what x and y is just with this given information? So think about that. What I'm going to do first is I'm going to, let's see, what should we do? Well, we can relate these guys by Pythagorean theorem, right? So x squared plus y squared is equal to c squared. That's our relationship here. And if we take the derivative of both sides with respect to time, we get 2x dx dt plus 2y dy dt is equal to 2c dc dt. Now, why isn't c constant here? Well, because the distance is changing. As x and y change, so is c. So, we're not treating c as if it's a constant, because it's not in this case. Okay. All right, let's see. So now all we really have here is dx dt. So what do we need? We need to figure out what c, y, and x are. If we figure out what these three things are, we're good, because we already know what this is. We already know what this is. And all we have to do is solve for dc dt. So how do we find out what x, y, and c are from this information? Well, we just have to look at the last sentence. They say, 2 hours later is the distance we're interested in. So, this car one, this green guy right here, is traveling at 60 miles per hour. And we're interested in how far he goes after 2 hours, right? We're interested in why. What is the distance after 2 hours? Well, that's just going to be 60 times 2, right? 60 miles in 1 hour. So in 2 hours, it must have gone 120 miles. Okay. What about x? What does x have to be? Well, we apply the same logic here. We're interested in where that car is 2 hours in its journey, and it's going 25 miles per hour at a very, slow crawl this car is going. And so in 1 hour, it goes 25 miles. Therefore, in 2 hours, it has to have gone 50 miles. So that's the distance of x, is 50 miles. Great. Now c, if we want to find c, we just do Pythagorean theorem, right? Because here's our triangle. We know that this is 120. We know that this is 50. We know that this is c. And so we do 120 squared plus 50 squared has to equal c squared. So let's see what this is. Put this in the calculator. 120 squared plus 50 squared. Square root of that. So we end up getting c equals 130 miles. Okay? So the stuff that we're plugging in, I'm going to box in purple. We're plugging in this stuff. We're plugging in this stuff. And we're finally plugging in c equals 130 miles. All right? So let's plug everything into our nice little related rates equation. So we have 2 times 50. Dx dt was 25. And again, I'm being lazy with units. You don't have to be, but y was 120. dy dt was 60. Yeah. Okay. Let me make some room over here. Equals 2 times c, which was 130, times dc dt. All right? Okay, so now I want to figure out what is dc dt. So to isolate that, I can just divide both sides by 2 times 130. And I'll just evaluate this in my calculator or in Desmos or whatever. So let's see what we get. All right, so I am getting 65 miles per hour. And that is my answer. That is the rate at which the distance of the cars is increasing with respect to time. It's 65 miles per hour. Okay, I think I'm going to stop the video here, and we'll pick back up on these last 2 problems in the next video. Thanks for watching, guys. An airplane flying at 450 kilometers per hour at a constant altitude of 5 kilometers is approaching a camera mounted on the ground. Let theta be the angle of elevation above the ground at which the camera is pointed. So let's go ahead and just draw a quick picture of, what we were just told. So we have this plane, and it's flying at a constant altitude. So the altitude that it's flying at is 5 kilometers. So that means that that's going to be the height throughout its flight is 5 kilometers. And since that is a vertical part, I'm just going to call this y. So that's going to be y. And we have this camera on the ground. Let's say it's this part right here. This camera. And theta is the angle of elevation with the ground to the plane. So let's just draw a quick sketch here. Angle of elevation, we are calling theta, so that's that guy, angle of elevation. And maybe I should do this like this. Let's do it like that. So here is our plane. Okay. All right. So far so good. Now it tells us that it's flying at 450 kilometers per hour. Now it tells us that the altitude is constant. The height is constant. So that just means it's kind of just, driving straight along horizontally. And so this is going to be, since, it's a horizontal speed, it's going to be dx dt. All right, we'll call this bottom part, we'll call that x. We're not really sure what that is, but yeah. Now, x is the distance, the horizontal distance from the plane to the camera. And as the plane travels along its path, the change in x with respect to time is decreasing. It's getting smaller and smaller because x is, again, the horizontal distance between the camera and the plane. So since that's getting smaller, we are attaching a negative to the 450 kilometers per hour. Okay, so we're given that, we did that, we got theta. Now it says when theta is equal to pi over 3, so I'll put that over here. Theta is equal to pi over 3. How fast does the camera have to rotate in order to keep the plane in view? So let's see what they're asking here. What does that mean? How fast does the camera have to rotate? Well, whenever we're talking about rotations, we can think about angles, right? If you think about, your unit circle rotating around the unit circle, your angle changes depending on how much you rotate. So what's changing is theta. Theta is changing. And it's changing with respect to time as it usually is. And so that's what we're looking for. We're looking for d theta dt, the change in the angle with respect to time. So let's use this information that we have to come up with an equation where we have theta, x, and y, right? We need those things. We need to relate them so that we can use our related rates. Well, if you remember from trig, we have something that tells us, explicitly what theta is equal to in terms of x and y. Theta is an angle, right? And if you remember, the tangent of theta is equal to y over x, right? That's from trig. Tangent theta equals y over x. Let's put a star here. That's from trig. Therefore, if we take the inverse of both sides, the tangent inverse of theta, or I should say, if we take tangent inverse of both sides, that's going to cancel at the left, and we just get theta is equal to tan inverse of y over x. So here we have it. We have an equation with theta on one side by itself and x and y on the other side. So we have a relationship here. And now we can use related rates. So theta is equal to tan inverse of y over x. And so, we're looking for d theta dt. So let's go ahead and take the derivative with respect to t of both sides. So we have d theta over dt. And so the derivative of tangent inverse is special. And it's special because, remember, we talked a little bit about these inverse trig derivatives. Let's write it over here. Let's write the derivative of tangent inverse is just 1 over 1 plus x squared. So one thing that we can do before we start, before we take the derivative of the right side, to make this simpler, we can just say, okay, well, y is constant. It's always flying at this constant altitude of 5 kilometers. So I'm just going to plug in 5 right here for y. And so if I take the derivative using the chain rule, right, because I have an inner function 5 over x and an outer function tan inverse of x, well, using the chain rule, what do I get? Well, the derivative of tan inverse is just 1 over 1 plus x squared. Okay, and then we're going to multiply by the derivative of the inner function. So, basically what you're asking yourself is, what is the derivative of 5 over x? Well, here we can just use the power rule because this is the same thing as 5x to the negative 1. Therefore, the derivative is negative 5x to the negative 2. Okay, so this is going to be times negative 5x to the negative 2. So let's see. Erase some of this and carry this down here. So, okay, let's just go ahead and multiply this on top to get negative 5x to negative 2 over 1 plus 5 over x squared. Now, so this is what we're looking for, d theta dt. Now, the question is, what is x? How do we figure out what x is? Well, we're actually given some information here. We're given that pi over 3 is our theta, right? And so we can sort of come up with an equation here. So the tangent of pi over 3, well, tangent of anything is y over x, right? Tangent of an angle. And so from the unit circle, the tangent of pi over 3 is the square root of 3. That's the ratio between the sides y and x. And in this case, y was 5, and we're looking for x. So if we multiply both sides by x and divide by root 3, we get x is equal to 5 over root 3. So now we can just plug that in to our d theta dt. And we can just put all of this in the calculator. So I know it looks like a big mess. But if we put this in the calculator, we end up getting d theta dt is equal to 67.5. Now, what are our units? We're talking about angles, right? And so this is going to be radians per hour. And that is our answer. A water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. So let's see what we have. Let's go ahead and just draw a picture of our cone, our conical tank, if you will. So here's our tank. And the radius of the tank is 2 meters. And the height of the tank is 4 meters. All right, so far that's what we have. Now they tell us the water is being pumped into the tank at a rate of 2 meters cubed per minute. So since we're dealing in a unit cube per time unit, this is dV dt, volume, the change in volume with respect to time is going to be 2 meters cubed per minute. Find the rate at which the water level is rising. So that is going to be the change in height with respect to time. So we're looking for dH dt when the water is 3 meters deep, when height is equal to 3 meters. Okay, so that's what we want to know. This is what we're given. So if you were to Google the volume of a cone, in case you don't have it memorized, you would find this relationship. We have 1/3 pi r squared times h, or you might see pi r squared times h over 3. It's the same thing. And so we have a relationship between volume, height, and the radius. Now, this problem takes a little bit more creativity. And the reason is because when the water rises in this cone, let's say the water is here. Well, the radius, the distance from the center to the edge, is a lot smaller than that radius up there, right? So what I'm trying to say here is that the radius is constantly changing, unlike the cylinder, right? The cylinder problem when we were filling up water, the radius never changed as the water height, got taller and taller and taller. The distance from the center to the edge was always the same, but not so with the cone, okay? And so what that means is that if we try to differentiate this, we're going to get way too many variables. We're going to have r, which we don't know what r is when h is equal to 3. We know what r is when h equals 4, but we don't know, what the r is corresponding to the h we're interested in, okay? So we're going to have a variable r that we don't have, that we can't find out. And we're also going to have a dr dt. Now, in the cylinder case, in that problem, dr dt was 0 because, there was no change happening with the radius. But here, the radius is changing. If we're right here, that is going to have a different radius than if the water level is this high, right? This is a different radius from this guy, is a different radius from that guy. Okay, so that's what makes this problem a little bit different from the cylinder problem. So what I'm going to do, if you want to, I'm not going to do this in this video, but if you want to, you can differentiate both sides, and you're going to get an r value, and you're going to get a dr dt value, which we have no way of knowing what that is. But what I'm going to do instead is I want to establish a relationship between R and H so that I can replace R in this equation with H. And so when I differentiate, I have everything I need. Okay, and so the relationship that I'm going to establish is using the idea of similar figures, okay? So in geometry, maybe I'll draw it up here. So here's our big cone right here. So this is our radius of 2, and it has a height of 4. And the relationship between these two quantities is going to be the same as the relationship between the height, at this time and the radius. So let's say this is our radius here. This is our height. We want to leave the radius as R because we're trying to say in general what the H as a function of R is, or R as a function of H rather. So what we do is we use the idea of similar figures here, which, is not completely an obvious thing to do, but it's how we are going to replace R right here in terms of H. So similar figures say that we can compare the parts and set them equal to each other. So in the big one, we have 2 is to 4, the radius is to the height, as in the small one, the radius is to the height. And now what I'm going to do is I'm going to multiply both sides by H to get R is equal to 1/2 times H. So that's the relationship between the radius and the height. So what I'm going to do now is I'm going to plug in, instead of R, I'm going to plug in 1/2 H in here. And I'm going to simplify this before I differentiate. Oh, I forgot my H. So this is going to be pi, and then we get times H squared over 4 times H. Simplifying this, we get V equals pi over 12 H to the third. All right. Now this looks better because we don't have R to worry about. Remember, R is not constant, so it's not like it's not as easy as a cylinder problem. But now what we can do is we can take the derivative of both sides with respect to time, giving me, let's see, 3 pi over 12, yeah, it's pi over 4, and then, we're just using the power rule here, dH dt. And now we have everything we need. We're interested when the height is equal to 3, dV dt is equal to 2 meters cubed per minute. So we get 2 equals pi over 4 times 3 squared times dH dt. So multiplying both sides by 4 over 9 pi to, cancel these guys out. I get dH dt is equal to 4 over 9 pi. Remember our units, this is the change in the height over the change in time. So our units for height were, what were they? Meters, and our time unit was minutes. So this is going to be meters per minute. And that is our answer here. All right, guys, that was the end of that problem. Thanks for watching. I hope that was insightful. As I said before, this unit and the last unit on optimization is as hard as Calc 1 is going to get. There is light at the end of the tunnel. Next week, after we do related rates, which is this unit, it's going to get a lot easier. So if you are having trouble with these problems, just know that that's completely normal, and these just happen to take more practice. But when you practice them a lot and really get the hang of it. It's actually pretty fun. So anyway, I hope this video was helpful, and I'll see you guys next time. Thanks for watching.